Hi, welcome to this new lesson. We have seen in the previous lesson how to manually create an image classifier where it was able to detect if the image was a vertical line or a horizontal line. The only problem was that in that classifier we were manually creating the filter ourselves. What we want to do right now is to create a more clever classifier. So this video is going to be structured in 3 steps. First, we're going to make a classifier which will detect if the image is vertical line or horizontal line, with the only difference that this time the computer is going to find the filter himself. Second, we are going to make something more advanced, more complicated. So instead of using just 2 images, we're going to use more images. And also we're going to increase the size of the image that before was 3 by 3 pixels. Now we're going to make it 5 by 5. Third, and the last step of this video, we're going to test the classifier with some image that the computer has never seen before. Let's start. Let's start by taking a look at the code that we wrote in the previous lesson, where we had the image classifier. The image classifier that worked in 6 different steps, where first we were simplifying the image by dividing it by 255. Second, we were flattening the image to be later processed. Then we had the filter that I created manually myself. Fourth, we had the convolution operation where we were going to multiply the flattened image with the filter. Fifth, the sum of the convolution. And sixth, the condition. So the condition, if was equals to 1, then we could say that the image was horizontal, otherwise the image was vertical. In this classifier, we created the filter manually. So I was trying different numbers until I got with this one that was working and was able to make a distinction between the horizontal image and the vertical image. Now, the difference that we're going to make in our new code is that the filter is not going to be created manually, but we want the computer to create the filter himself. So we're going now to write this function in a small different way so that we can take the filter out of the function and then the computer can find the filter. So let's start with an empty file. First of all, let's import the libraries. So we import cv2 and then we import numpy as np, and we're going to load the same image that we used before. So let's just load like the vertical image. img is equals to cv2.imread, and then we're going to take the image from images and we take vertical.png and then cv2.imread grayscale. Now, to make sure that the image we're loading correctly, we're going to show the image. cv2.im show. We're going to show, okay, let's call this image, and then img, but we're going to resize img because it's too small, it's only 3 by 3, so we wouldn't see it. So cv2.resize, we're going to resize img. Then we define a size of 500 by 500, so it's big enough that we can see it. And remember to put interpolation 0, so there is no filter applied to the resizing of the image. And then cv2.weight key 0. So we can run this one. And now I have the vertical image. Now let's start building the classifier. So let's start doing the first pre-processing operation, which are to simplify the image and then flattening the image. First, simplify the image. So emg is equals to emg divided by 255. So the pixels are going to be either 0, either 1. 0 black, 1 white. Then we're going to flatten the image. So flatten the image and flatten image is going to be equals to emg.flatten. So if we print flattened image, this is going to be our vertical image when it's flattened. So all the pixels, all the values of the pixels are going to be in a row. We need to do this operation for each image that we need to preprocess to be classified. So now let's make this into a function so that each time we don't have to flatten even the second image. So if, for example, now I load the horizontal PNG, I will have to do the same for horizontal. So divide EMG horizontal by 255, then flatten the image, and so on. So let's put everything in a function so that we just take the path of the image and we will get, as a result, the flattened image. So let's do that right now. Simply, we can do this. Def preprocess EMG, and here we're going to put the path of the image, path EMG, and let's select all the text from EMG to flatten image, and let's press tab. So everything that it's here, it's inside the function preprocess image. And then we want to change path EMG like this one, so that each time we can change the path of the image, and we're going to return the flattened image. And of course now we don't have anything to show, so I can comment these two lines. And now let's try this code. So we have EMG, flatten EMG. EMG is going to be equals to preprocess EMG, and I will put the path of the vertical image, EMG images, and then vertical.png. So if I print flatten EMG, I run the code. Now we have right away with just this function our vertical image into one row. So flatten image is this one. If we load the second image, so let's say this flattened image will be the vertical, so flatten vertical, and then we have also the horizontal, flattened horizontal is equals to preprocess EMG, and we will put the path of the horizontal image, then horizontal.png. And so if we print flatten vertical, and then we print flatten horizontal, and we run this, we see just two simple lines, and we have the vertical image and the horizontal image in just one line. Now let's move on. The next step after this was to multiply the flattened image by the filter. The only thing was I created the filter myself. So filter images, it was something like this. So it was 1, -1, -1, and so on, and we had 9 numbers. We had 9 numbers because 9 are the pixels of the images. So flattened image has 9 pixels, and of course also horizontal image has 9 pixels. So the filter has to be equal to all the images that we want to process. I created the filter manually with trial and error. So I tried some filter which didn't work, so I changed the values inside until I got something that it worked. Let's now create a filter automatically. So we have a function mp.random.randint. So we're going to use only integers, so like 0, 1, 2, and so on, and we will not have like 0.5 or something, just only integers, so something really simple. We will start from -1 until 2, and the size is going to be equals to 9. In this case, -1 is included, so we have values of -1, 0, 1. The 2 is not included, so it will start from this one included to 2 which is not included, so -1, 0 and 1. So if I print filter images and I run this is our filter. So 1, 0, -1, -1, 0, 0, -1, -1, 1. I run this again, 0, 0, 1, -1. Let's run it a few times. What you can see is that each time I run the code, the filter is different. The filter is different because we simply are using random integers. So each time the filter is different. Having each time a different filter means that we never know if the filter is going to work or not. So let's go ahead and now let's apply with this filter the convolution operation. So we're doing the convolution with the vertical. So let's say convolution vertical, and is going to be equal to the sum of the vertical image multiplied by the filter. And we do the same for the horizontal image. So we have the convolution of the horizontal image, convolution horizontal is going to be equal to the sum of flattened horizontal multiplied by the filter. And let's print right now. We're going to print convolution vertical, and then we print convolution horizontal, and we can run this one. Convolution vertical is 0, convolution horizontal is 0. Let's also print the filter so we know which filter is going to work. Print filter, and then filter images, and let's run this. So this filter is going to give -1 for the vertical and 0 for the horizontal. Is this a good filter or not? We can say, at least for the moment, it's a good filter because it is able to detect some difference between the vertical and the horizontal line. Let's try running this a few times. So now we have 1 and 1. So this filter, which starts with -1, 0, 0, 1, 1, -1, 0, 0, -1, doesn't really distinguish from the two images. So whether we give the vertical image or the horizontal image, it's going to return always the same value. So we can really classify the images using this filter. So to understand which filter is good or not, the only distinction that we can make is if there is some difference between the convolution of the vertical and horizontal, then it's a good filter, otherwise it's not a good filter. So we can say this: if convolution horizontal is different than convolution vertical, then we can say good filter, otherwise else print not good filter. And let's run this a few times. So we got a good filter, still a good one, a good filter. So we're running, okay, we're running until we get a not good filter. So 0, 0, this is not a good one. So if you notice right now, each time we try, sometimes we get something that works, sometimes we get something that doesn't work. But in real life, we can just take this as good filter always. So we cannot just guess and hope that the filter will be good, but we need to have some way that the filter will be always good. So can you guess what operation are we going to do right now to have always a good filter? One simple approach, really simple, will be just guessing until we get a good filter. So we get the filter, then we test if the filter is good. If the filter is good, we can take the filter and use that one to classify the images. If the filter is bad, we say the filter is not good, so let's try a new filter. So we keep looking for new filters until we get a good one. So what we do right now, we use a while loop just before filter images, while true, and then let's put all the code below inside a loop. This loop is going to be an infinite loop, so it will keep always looking. So I will run this, and this will run infinite until I stop it. So you see we get good filters, but also not good filters. So as our idea is to stop only when we have a good filter, so we can say that if the filter is good, we can show the filter, good filter, and we break the loop. So if the filter is good, there is no point to keep looking. If the filter is bad, we don't need to print this. We don't need to print this not good filter. Just keep looking for a new one. And that's pretty much what we have to do. And we can run the code. Okay, I'm printing also twice the filter. I've just noticed. We can remove this. We need to print the filter only once. Of course, we will get always a good filter, so where gives always different result, because we keep looking for a good filter. How many guesses are there before we get a good filter? Right now we don't know, but we can count them. So let's count and see how many guesses we have to make before getting a good filter. So we can say count equals to 0 outside of the loop, so we'll start with 0, and then each time count plus or equals 1. On each loop we add the count. So this is count 1. We are trying this filter. If the filter is not good, the loop will start again, plus or equals 1. Now the count will be 2, and then we try this filter. If the filter is good, it will print. We have good filter, we will print the filter, and also we can say attempts, and then here we have the number of the attempts, which is the count. So this way we can see how many attempts we had to make before getting a good filter, and I can run this. So we were lucky, we got a good filter the first attempt, always still the first. It seems that it's really easy, and we almost always get a good filter on the first attempt. And just okay, now we got a good filter at the second attempt. So it's not always, it's most of the time easy to get a good filter. And also it's easy to get a good filter because the images are quite different. One is a just vertical line, the other one is a horizontal line. So in this case, it's really easy. Even just by guessing, it's really easy. Considering also that I was able to detect, to make manually a filter that could work. So that's why we can find so many filters easily. For the first time now, we have a method that automatically detects the filter and that we can use to classify our images. To make sure that this really works, just not in theory but also in practice, we're going to test it right now. So what I do, I run this code and we get the filter. So if the filter with this filter, if it's equals to 1, it's supposed to be the vertical. So if it's 1, is vertical, otherwise the image is horizontal. So I'm going to copy this one, then I will switch to another tab. So I just switched to the tab that we created in the previous video. Do you remember where I created the filter manually myself? Now instead I'm going to put the filter I've just got right now. So I just need to put the comma between the numbers. And so I said if the convolution is equals to 1, the image is vertical. So in this case, the condition is going to change. So as we have different filter, also the condition is going to change. Horizontal. And let's test now the filter. Here I have a few images that I loaded before. So we have vertical, horizontal, down horizontal, left vertical. So let's try with the first one, which is the vertical. So we try the function classify image. And as a result, if everything is correct, we should get vertical. And let's run this and we get vertical. So far it's good. Let's try with EMG2, which is supposed to be the horizontal one. So EMG2, I run this one and we get horizontal. So we're sure that with this it works because we tested them. Let's now try other images. So we have the down horizontal, which hasn't been tested with this filter, so I'm not sure if it's going to work. So we get down horizontal and the result is horizontal, so now it still works. And EMG4, which is left vertical, and we run this one and we get horizontal. So the filter worked well with the first two images that we already tested. When we can say that we were sure that it will work correctly with the vertical and horizontal, but as we change a bit the image, this filter seems not to be good enough to detect and classify horizontal and vertical images. How can we improve this? Well, one idea would be to have not only one vertical, but to have more verticals. So we had a vertical white line in the center. Instead, we could have also vertical white line on the left side and on the right side. So we can be sure that the filter gets tested with all the images, and only after it's tested with all the images, then we can be sure that we found the one that works correctly. And we're going to do some operation like this right now, but I want to make this more challenging. As we already know how to make a filter manually, how to create a random filter automatically, let's make the thing more difficult. So now I created a few images which I'm going to load, and we will start with an empty file to load these images. So I will start with this empty file and we import CV2, we import numpy as np, but also I'm going to import a new library which is called glob. I'm going to use this library to take multiple images from one folder. So in the folder images, I put 5 images of squares and 5 images of crosses, and I'm going to separately load them. So first we're going to load the squares, and it will be equals to glob.glob, and we need to put now the path name images. All my images with the square have the name square with different numbers. So we have square 1, square 2, square 3, square 4, square 5. So in this case, the way to find all the files which starts with the name square only is to put square, which is the same for all of them, and then this asterisk, which is the value that changes, .png. And now we can print squares to make sure that this is correct. And here I get square 1, square 2, square 3, 4, 5, which are the images that I have on the folder. So if I show quickly the folder, I have more images. I have cross 1, cross 2, cross 3, cross 4, cross 5, and then squares 1, 2, 3, 4, 5. And now we can say for img path in squares, and we can load all of them. cv2.im show, no, im read first. We need to read the image. The path is img path, and we want to load image into grayscale format. So img, and then cv2.im show. The title, we can put the image path as title, so it's different for all of them. We can show them at the same time. Let's remember to resize the images. This one is really small and we wouldn't see them if we don't resize them. img, the size, we will make them 500 by 500, and then interpolation is equals to 0. At the end of the script, out of the loop, we put cv2.wait key 0, and I can run this. Here I have a few different squares. We can see them here, and also I have a few different crosses which I'm going to load right now. So crosses is equals to glob.glob, same as before, images, except that instead of square we will put cross and then asterisk and then .png, and we loop through the crosses and we run this. So I have different crosses of different sizes and also a bit different shapes. So this one, the sides have exactly the same length. They take all the height and all the width of the image. In this one, they have the same length, the both sides, but they are really short. So they take less than around more than half of the image. In this one, the height is longer than the width, and this one is the opposite. The width is longer than the height, and also the central part is just more on the right side instead of being in the center. So we have many different types of crosses, and we all might agree that all of them are crosses. So we don't test like we did before, vertical and horizontal line, just one vertical and one horizontal, but now it will be much more challenging for our classifier to work with them. And also I have to add that now the size of the images are different. Before we had 3 by 3 pixels, and now we have 5 by 5. So it will be 1, 2, 3, 4, 5 pixels of width, and 1, 2, 3, 4, 5 pixels of height. We're now going to implement the same code we did before to be able to detect a filter that will work with all the images. Let's start. I will go back now to the previous code and I will copy the code right here, and then we can integrate the code with loading multiple images. So I've just copied the code I wrote at the beginning of this video, and I'm going to paste the code right here. Where we have the function to pre-process the image, we can leave this function at the beginning, like this, and then we can adjust the code with what we have right here. So we don't have to work with the flattened vertical and flattened horizontal, as we don't have them. We're not going to work with them. The convolution, we don't have to make the convolution. And we can remove actually almost everything. We can just keep the function preprocess emg, and the rest we can pretty much write everything. So we have the count, the while loop to keep looking until we get a new filter. Here we increase the time each time we are on a new loop. And here we have the filter, so a random filter. What's the difference now? The difference is that the filter has a different size. Before the filter was 9 pixels, now it's going to be 25 pixels. 25 pixels because 25 is the size of the images, and we can see them right now. We don't need also to load and show the images anymore, so I can maybe not remove. I will comment this code, maybe we might need that later. Also this one, instead we want right away the flattened image. So if I have for the crosses, we will say flatten emg is going to be equals to preprocess, which is the function that we created before, and we want to preprocess emg path. So we have 5 crosses, and we can check now them. Let's run this. So here is the first one. Of course, this is just one array. It's just the representation. It's made in this way when we print it, but it's just one array. This one, the same for this one. So here we have the 5 different crosses, and here we have 25 numbers. That's why also the filter needs to be 25, and we have 5 of them because we have 5 pictures of the crosses. If we had more pictures, then of course this will be as many arrays as we have pictures. And we can use this one right now inside the loop just after the filter, and we can put it here. And also, okay, I can remove this. So first we check the crosses here. Okay, now let's add the squares. Let's put it just here. And we have the squares. So for image path in squares, and we have this. And now let's start with the convolution of the squares. So convolution is going to be equals to the sum, and then we're going to multiply each flattened image per the filter, and we can print this convolution, so we will see the results that we get. So print squares, and let's run the code. Okay, this is an infinite loop. So let's break the loop just right away. So we will run it just once to see what results we get. 0, 4, -3 to 4. So with this filter we can also print filter and then filter images. Let's run it again. Of course, now the results are different, as different is the filter. With this one, these are the results of the sum of the convolution for the squares. And let's do the same for the crosses. So we print crosses, and then we we make the convolution, so I will code this exactly the same operation. So I can just copy this code and then I can print convolution. Here we have squares 0, -2, 1, -4, 0, crosses 0, -3, 2, -2, 0. Now you can see that this thing is much more challenging than before. Before we simply had just two numbers, now we have as many as are the images. And of course, considering that the images are different, also each square is different from the other squares, so we will not be able ever to, or almost ever, to have the same number for the same square. Here it happens just that the last square has the same value of the first, but it's really rare that something like that happens. But also some cross has the same value like that one, similar or the same of the first and the last square. In this case, our condition function needs to include more ranges. We cannot say just 0, -2, 1, -4, 0 are squares and 0, -3, 2, -2, 0 are crosses. We cannot say this way. Instead, let's try to make some ranges including more numbers. So one easy way will be to say if the value is equals or greater than 0, then it's a square. If the value is less or equals to not equals, if it's less than 0, then is a cross. So how can we do this? First of all, let's not break the loop anymore. Also, now we want to keep the loop active, so if we print everything, of course we cannot read all the things that there be printed, so let's stop with the printing. Also the filter, we don't care right now about the filter. Instead, we want to put a condition. So our goal is that all the squares are let's say greater or equals 0. So we do the opposite operation to break the loop. Let's follow this one carefully. We say if convolution is less than 0, we break the loop. So in this case, we want all the squares to be greater or equals 0. So if they're all greater or equals, the loop keeps going and the filter is good, we don't do anything. If we find some square that is less than 0, it shouldn't be less than 0, so we break the loop because the filter is not good. We want to have a new filter, so we should look for a new filter. Now we need to find a way to keep track that everything is fine. So we can say something like this. We need to be able to put a switch to break the loop. So for example, good filter is equals to false before the loop. As long as the filter is bad, so as long as good filter is false, we keep looking for the filter. So while good filter is false, we keep looking. Here we looped through the images. So for img path in squares, we know we have 5 images. So if we are able to get to the last image without breaking the loop, we are also able to understand that all of the images were fine. So the convolution for each image was greater than 0. How can we understand this? considering we have 5 images of squares and 5 images of crosses, we should find a way to load them and be sure that we're able to detect when all of them are processed. So in this case, we can do something else. We can change the way we load the loop. Instead of loading for EMG path, we say for I in range of 5, because 5 are the images, and then the process path, the path of each image we take from squares, so the index is I, and we can try this to make sure that everything works. Let's print convolution, and let's run this. Okay, everything is working. So if everything is greater or equals to 0, it keeps looking through all the images. When we get to the index 4, if I is equals to 4, because when we say in range of 5, it starts from 0. 0, 1, 2, 3, and 4. Then if we get to the index 4, it means that all of them are greater than 0. So if the index is 4, so in this case, we can say that good filter is equals to true. And if a good filter is equals to true, of course the loop is going to break. So out of the loop we can print the filter, and we don't need anymore this one. We can print filter and then filter images. And also let's print the attempts. Print attempts, and then we print the count, and let's run this one. Just 2 attempts for 14, 10, 25, 7, 3. It seems that quite easily we're able to get a good result. So that means that with this filter, each time we use this filter on the squares image, is going to be there as sum always greater or equals 0. Let's now add something else. Now the filter is able to detect with result greater than 0 all the squares, but what about the crosses? All the crosses needs to be under 0. So now we need to work with the crosses. So we will add convolution 2 is going to be equals to the sum of, we need to load the crosses, of course. So we have flatten image 2. So flatten image 2 multiplied by filter images. And of course we need to do the same but opposite operation that we did for the squares. So we can say if convolution 2 is greater or equals 0, then we break. So what happens? If all the squares are greater or equal 0, they are fine, so we keep going. If all the crosses are less than 0, so we don't break the loop if they are more or equals, then it can keep going, and only in that way we are able to get to the end of them. So if I equals 4, which this I equals 4 is like the length of the images, then we can say that we found a good filter. And the filter is going to work to classify all these 10 images, the 5 squares and the 5 crosses. Now, the moment of the truth, we will be able to find a filter. Who knows? Let's run the code and let's see. And this might take a long time, as there is quite a lot of tests and attempts that the script has to make to find some filter, like long 25 numbers that can work for all the 10 images. So I'm going to leave this one, and I will pause the video until we will get to some conclusion, hopefully. It took maybe 30 seconds more or even less, not so long. Anyway, we found a filter, and to get this filter it was necessary to make 108,280 attempts. It's quite a lot to make so many attempts for such simple images like square and crosses. But at least, even if it took a lot of effort for the computer, at the end, the computer was able to find a filter which is able to classify the squares and the crosses. And now we're going to test it. So I will copy this filter, and of course you will have some different filter if you are calling also yourself this part. So I'm going to copy my filter. You can copy your own filter on the same function to classify the images, and we're going to test whether it is working well or not. So here we have our function to classify the image, and here I will paste the filter that I've just got after 100,000 more attempt, comma after each number, okay, it was almost perfect and I missed it at the end. Okay. Anyway, this is the filter, and the condition that we decided before was if the sum of the convolution is less than 0, it was a square, otherwise a cross. And let's try this one. I'm going to load from images. I will load square 1, and here is EMG, and let's show the result. Okay, it's a cross. Maybe the condition was different, was the opposite. It's a cross. If it's less than 0, then it's a cross, otherwise it's a square. And I will run this, of course. Okay, this is a square. Let's try with square 2. It's a square, square 3, the result, it's a square, square 4, square. Let's try some random cross. So cross 1, it's a cross, cross 3, it's a cross, cross 4, it's a cross. It seems it's working well with all the images that we use like training to get this filter. What if we put some cross or some square that we never had before? That's what I'm going to do right now. So I will draw right now a square. I'm using now GIMP, the image editor. Let's draw some square that we don't have. So we didn't have such square before. Let's export this image test. So I put it in the same folder. Here I have image test. somewhere. This one is the square that I just created, and I'm going to load image test. So if everything is correct, it should say this is a square, and it seems that this so far this classifier doesn't perform so well with images that has never seen before. Let's try create some crosses. Okay, we don't have such cross, so I can put this one, and okay, this one is a cross, is detected correctly. Let's now try drawing a square like this in the center. Export to image test, or you can run this, it's a square. And also I can show like visually what the code sees, so to make sure that we are loading exactly the image that I'm saving right now. So if I can do this, CV2.im show, and I'm going to show EMG and then EMG, but of course we need to resize the image. CV2.resize EMG, then 500 by 500, so we can see interpolation 0, so no feeders, and of course CV2 weight key, CV2.weight key 0, and the result we need to print it right here. And I can run this. Okay, that's the square that I've just saved, and it's a square. I'm going to try with a couple more examples, and that will be enough. Let's maybe draw some cross. Like this one. Export to image test. We run this, it's a cross and it's detected correctly. Let's put this one. This is a strange cross. We don't have an example like this. Replace, and still detected as a cross. I want to try with some other square, and that's all. That's square, so maybe like this. Export square, that's correct. And let's make some square that doesn't really exist. Okay, just one part of the square. Let's challenge this code. Export to image test. Okay, this will be also part of a cross, so I don't really know what we're going to get. We will get cross, and if I add this, export to image test, and still we will get cross. In conclusion, regarding this lesson, we learned how to find the filter automatically, but just random trying filters until we get something that can work. We learned that this is an approach that somehow gave us some interesting result, but also we learned that there are drawbacks. Once it takes really long time, like just trying randomly, it took us around 100 and plus 1,000 attempts to work with only 5 images per class. So can you imagine with thousands of images, or if we have bigger images than just 5 per 5 pixels, this will just be impossible to work with. And also we could notice that just placing the figures like the rectangle or the cross in different positions, already this code was not working correctly and was giving us false result. This is some kind of really dumb automatic classifier, and we will see in the next lesson how to improve this more so that it can be more clever and try to learn from its mistakes. This is all for the moment. See you in the next lesson.